What's going on, everybody? This is Mr. Diamond. As you can see, I'm back in the classroom. I am not going to be using a good mic, unfortunately, anymore until I can find a cheap one to bring. My mic broke from bringing it back and forth to school, and I have my good mic, but I'm going to keep that at home. So I'm just going to tell you that in advance, that the audio quality is going to suck if you see me at school, unless I give you an update after that. So we're going to be starting Chapter 3, which is about forces. And starting this chapter, things are going to probably be a little bit different. I'm trying to figure out a way to frame this class and to work with this class because I just feel like it's really difficult for both of us to really be getting a lot of it out of this, both me as the teacher and you as the student. I feel like I want to try to do things a little differently. So while I was on quarantine and taking care of my wife, I took the time to kind of tweak these notes a little bit and hopefully make them a little bit more understanding. This is going to be basically 2 days worth of notes that we would have done in class. So there will just be kind of a short activity for you to do during the week when you're not here. Just kind of I'll be discussing these notes and going over them a little bit in this video. So we're going to start with Newton's laws. You guys already should have watched a YouTube video that kind of went into over this a little bit, but we're going to focus in on them and give you kind of the definitions and the information that I care about in relation to them. These last two chapters have been all about kinematics, which if you remember, that's the description of how objects move. But we're going to now be looking at dynamics, which is kind of the why objects move, the things that involve forces. A force, as we know it today, is any kind of interaction that affects the motion of an object, and we treat this as a vector quantity. Because if you push something or you pull something, like if I take my can of Monster that is over here, and if we're going to pretend it was on a flat level surface, when I push it, I am applying a force that has a magnitude and it's got a direction. I'm pushing it this direction. In this case, I'm pushing it to my left. When a force occurs due to two objects that are coming into contact, like me pushing on my Monster can, we call that a contact force because it's actually something that is in contact with that object. There are also forces that occur without touching. We call that action at a distance forces, which is, I guess, a lot better for social distancing than contact forces are at this point. But this is going to be things like electromagnetic forces, gravitational forces, and magnetic forces. We're going to do a quick, just brief run through of history talking about forces a little bit here. This might show up on the test, no guarantee that it does or doesn't, but this is just kind of some interesting how we got to the point of where we were at. So Aristotle was the first person who proposed a system that we would actually call like modern day forces. He broke it down into three categories. There were natural forces, voluntary forces, and forced forces, or these were motions that could occur. Natural motions were things like dropping something. If you drop a pen, that is a natural, a thing returning to its natural state of being back on the ground. So that would be gravity. And then also things rising, like if you had a balloon filled with helium, although Aristotle didn't really have a whole bunch of helium canisters around back then. But anything like filled with helium or something that's like a leaf that gets picked up by a piece of wind and it goes up, that thing that is just kind of rising, I guess the wind would be doing the force in that one. But helium balloons is the best example I've got for this one. That would be rising due to levity. Levity is the opposite of gravity. Now, voluntary forces would be things like humans and animals. We can make ourselves, we can choose to move ourselves. Birds can flap their wings to fly. Humans can put their feet on the ground to walk or run. Those are all voluntary forces. And then forced forces are things like pushing, pulling, ripping, tearing, yanking, yeeting. Any of those things would be forced forces. He didn't really call them forces because calling it a forced force would be a little bit weird. But he classified them as that. There was a little bit of issues. Most of the problem involved the fact that they felt like you had to continually apply these forces to things for them to continue. But that doesn't actually logically make sense because, for example, that would mean that when you fired an arrow, you have imparted some force to it, and it's going to continue with that force. And once it's no longer being subjected to that force or it runs out of energy from that force, you would expect that it would just drop. There's no longer anything moving it around. And arrows don't do that. It's not like when you fire a gun or an arrow, it just flies through the air, and when it gets to a certain distance, it just like flattens off. It's going to arc like our projectile motion. So there were some problems with the way that they were describing it back then. Galileo gets credit for proposing that objects could exist in motion as a natural state. He was the first person who really had that idea. Everyone at that point, up to that point, had mostly said that motion was something that needed to occur or needed to have something imparted to it, and that most things in nature would tend to prefer to be stationary. They could say, for example, this is kind of the argument that he used to explain how something could exist without the need of force to be moving, would be, let's say you had a book on a table, and the smoother and smoother you make a table, the easier it's going to be to push and pull and move that book around. So if we could continue making the table smoother and smoother and smoother, and today we would think of like an air hockey table where there's actually that cushion of air, there is like no friction whatsoever. And so just a simple nudge could cause it to move, and it would continue moving non-interrupted because there would be no friction, there would be no forces impeding it. And so it doesn't need to continue having forces added to it. If there's no force to oppose it, it will just continue forever. So if you had, for example, picture a vast, empty, like frozen lake. The lake is completely solid, completely frozen, and completely frictionless. Some of you might think this is what your soul feels like at this moment, but I kind of relate to that. But we're going to have this vast icy lake, and if you were to set something on the edge of the ice and you were to give it a push and there was no friction, that object would continue just going forever unless something else impeded it. So that was where Galileo came up with the idea, well, that you don't necessarily need to have a constant force being applied to something to keep it moving. You just need there to be nothing stopping the force that was initially applied from dissipating or from going away. Newton, in his book Principia, or the long version is right here, Philosophiae Naturalis Principia Mathematica. This was Newton's book. That was my very American bastardization of that pronunciation there. But he acknowledged Galileo as the inspiration for his theories of motion, and he came up with what you probably think of when you think of forces, which were Newton's 3 laws of motion. However, they are a sum of many scientists' works and ideas. He just kind of phrased them a lot better than most other people did. So don't think that this was like Newton just chilling by himself coming up with this stuff. He does get credit for being able to phrase it and to combine all the ideas, but there is a lot of people involved in this concepts. So Newton's first law is actually just a wordier version of Galileo's conclusion. Galileo felt like if you had like a vast frictionless surface, you could push an object and it would continue moving. And Newton put that into a little bit more of a scientific phrasing, which was every object continues in its state of rest or uniform velocity in a straight line as long as no net force will act upon it. So this is sometimes called the law of inertia. Inertia is the tendency of an object to resist a change in state. Or a change in state in this case could be, if it's still, a change in state would be starting to move, and if it's moving, a change in state could be either slowing down, speeding up, or stopping. The tendency of an object to basically keep doing what you're doing, to keep calm and carry on, as it were. And his idea was that if you have an object and it is moving, it will keep doing that until some type of force interacts with it and stops it from doing that thing. Now, thankfully, in the real world, we have lots of forces that do that. We have people who can stop things. Cars have brakes, which freeze the tires, which cause friction to occur and cause it to cease the car's motion. There's all sorts of things. Magnets, electricity, like there's a bunch of things that can be used to kind of add a force to something to stop it. Same thing with getting something going. You can push something, you can pull something, you can use your advantages with friction and the normal force, which we'll talk about later, that you can use to actually push your feet off of the ground and move. All of those are examples of Newton's first law. And inertia just means that objects will want to keep doing what they are doing. So how do we measure this inertia? Well, actually, you already have been doing this. You've probably been doing this for a long time now. It's mass. Newton originally used mass as a synonym for quantity of matter, which is probably what you think of mass as from like your science classes. But we now really in science think of it more as a measure of inertia of an object. It's not a measure of the amount of matter, it's the inertia in that object. And this should make some sense, even though that's kind of a weird way to phrase it, because bigger objects are harder to start moving, to keep moving, or to stop. For example, if I have like this very small napkin or paper towel that I have wadded up, it has a very low mass, which means it has a very small inertia. And that means that it does not take a lot of force for me to get it to move around. I can kind of fling it all around very easily, just bopping it into the air, and it goes flying all over the place. But something that's heavier, like for example this bottle of water that's mostly full, it has a lot more energy. And so if I kind of apply the same amount of force to it, it has a bigger tendency or a greater tendency to stay what it's doing. I'm going to have to put more energy to convince it to move, and that's because it has a higher mass, which means it has a higher inertia. And then you could also blow this up to things like a car or a train. They are gigantic, they have a large amount of mass, and that's also why they take so much energy to get them moving. You could walk up to this water bottle and push it over, or this napkin, and you could push it over. But if you go up to a train, I assume most of you probably can't walk up to a train and physically move the train just by getting it going, because it has a large mass, and therefore a large tendency to stay still if that's what it's already doing. Now, this tendency of objects to keep doing what they're doing actually pops up way more than you realized. If you've ever been in a car and as you go around that corner, you feel yourself kind of get pulled to the side or pulled to the side depending on which direction you're going, that's inertia. Your body is trying to continue going in a straight line and the car has moved away, so your body gets tilted away from the direction that the car is moving because your body was continuing to move that direction. That is the inertia of your body. If you're in an elevator and you get that weird feeling when it stops moving, like you're going down and then it stops and you kind of feel like like your body just drops slightly, or you're going up and then when you stop you feel like your blood kind of rushes up or rushes through your body, that is your blood and your organs having inertia. They're trying to continue. As you go up, your blood and your organs are going up, and when you stop, it will continue for a very brief moment and will continue attempting to move upwards, and it may feel like the blood rushes to your head, or when you go down, it'll feel like it rushes to your feet. In movies where people crash through windshields in a car wreck, like they're going at a high speed and they hit something without a seatbelt and they go flying forward out of their car, that's inertia. Shaking a sauce bottle, like if you had like a bottle of ketchup and you hold it upside down and you shake it, I'm glad this thing has a sturdy lid. I didn't check to make sure it was screwed on completely. When you're shaking it, what you're trying to do is you're pulling it up, and then when you push it back down or when you move it back down, the inertia, the liquid that's in the bottle is going to stay where it is for a brief moment before it begins falling, and your goal is that you're going to continue that falling motion and make it fall out of the bottom of the bottle. So inertia pops up a lot in our day-to-day life. One final note for this law is that we have to be careful that mass and weight are actually different from one another. And this is really easily to be confused, and we may use them interchangeably in our day-to-day life, and I will probably, because I'm a hack and a fraud, I will probably use them interchangeably in class at least one point. Mass is a property that an object actually has, but weight is actually a force that is acting upon that object that is based on the mass. And so what I mean by this is actually why your weight changes if you go to other planets. Your mass remains constant. Your inertia, the tendency of your body to continue doing what it's doing, will stay the same. Or if we go back to Newton's original idea, the amount of matter inside of you will remain constant. But if you go up to the moon, for example, the gravitational pull of the moon is so much smaller that your mass is being pulled at a lesser extent. And so the force acting on your mass, your weight, becomes different. The other ways that you can kind of word this, your mass is scalar, but because weight is being pulled downwards towards the gravitational center of wherever you're at, we would call that a vector. Mass can never be zero, but you can have weightlessness. If you've ever gone on a roller coaster and you get to the top and you feel that brief moment like you're floating, or if you're ever lucky enough to go on any of those like the Vomit Comet planes that do to the 0 Gs, or if any of you go on the bright future that I know you will and become astronauts, that feeling of floating around there, you still have mass, but there's not a gravitational pull on you, so you don't have the force that is making you experience weight, so you are weightless. Mass is also usually measured in the SI unit of kilograms, but weight is measured in physics, at least in newtons. Now, you probably don't measure your stuff in newtons. It's not like you have a scale at home that tells you that you weigh like 14,000 newtons or something like that. I actually don't know if that's a large number or not. Newtons are weird. It's hard to get a a framework on what they actually are like. I think 14,000 newtons isn't that unreasonable for a person, but we don't use pounds or ounces or anything like that. And in other countries, they use kilos to measure their mass, but really they're just measuring the mass of themselves on, or it's a little bit differently. They're not usually going to measure themselves in newtons. So really, if you have other countries who think we're dumb for using pounds, they want to get really technical. They should be using newtons to be like accurate in their SI units. Okay, Newton's first law involves situations where there's no net force acting on an object. So what do we do if there is a net force? Well, that's where Newton's second law comes in. A net force will change the velocity of an object, whether increasing it or decreasing it, or changing its direction. And there's going to be a small demonstration that I'm going to have us do in class. We're going to work out and we're going to look at involving an ice skater. And that will kind of show you what we're talking about here. But basically, we know that a change in velocity must mean that acceleration is occurring. And we also know that we can relate mass to that change in velocity. Objects are going to want to stay the same or doing the same thing. If you're making it accelerate, you must be providing some type of force. It takes more force to move an object with more mass, so mass must be related to this velocity changing, to this acceleration, and therefore to the forces that are occurring. So we'll be doing a web activity that kind of shows what we're talking about here, but we can kind of wrap this all up in an equation that you've probably heard before, which is that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to the object's mass. The direction of the acceleration will be the direction that the net force is acting on an object. Make sure you realize that it says net force. It doesn't mean that all of the forces are acting in that direction. It just means that if you vector summed all of your forces together, you should have a net force pointing the direction that the thing is accelerating. Or in equation form, we say that the sum of the forces is equal to the mass times the acceleration, or F equals ma. Newton's second law, you're going to be using this for most of the problems this chapter. If we use kilograms for mass and meters per second squared for acceleration, we get this really odd-looking unit of kilograms meters per second squared. That's what we call a Newton. That's what we give him enough credit for this that we have decided to name this unit of weight, this unit right here of force, to be a Newton. Now, notice that I said unit of weight, unit of force. That's because, again, your weight is a force being acting upon you. It's a force that you are feeling, so that's why we describe them in newtons in physics. I've got some examples here that we'll work out in class together, and we'll make sure that we actually kind of go through them together, but they're pretty straightforward. Well, with the acceleration, if you applied a force of 2 newtons to a 0.50 kilogram object, ignoring wind and friction. And then a more complicated example is, what is the average net force required to bring a 1,500 kilogram car to rest from a starting speed of 100 kilometers per hour in a distance of 55 meters? So that one you're going to need some of your equations from the last few chapters to solve that one. Newton's third law is one that you are likely very familiar with. I'm going to back this out, and we're going to make that highlighted because I'm trying to get better at highlighting the vocab terms, so you can do that. There we go. Pretend that didn't happen. Newton's third law is one you're very likely familiar with. For every action, there is an equal and opposite reaction. You've probably heard that at some point in your life, and it's probably popped up way more than once, honestly. But that phrasing is a little bit problematic. Like, let's consider that you're sitting in a chair. Your butt, or in my example here where I'm sitting in this chair, my butt is exerting a downward force upon the chair due to my weight. My mass on this planet is being pulled downwards to the gravitational center of the Earth, causing me to have a downwards facing force, a force that is positioned or pointing downwards, that is pressing me to the seat. However, usually when you're sitting in a chair, like right now, I'm not accelerating. You don't just sit and continue falling through the chair, so there must not actually be a net force, because if there was a net force, based on our equation from Newton's second law, a net force would mean that our mass was accelerating, and I'm not currently accelerating. So there has to be something preventing me from going downwards. There needs to be another force, another vector that's pointing in a certain way, or that's angled in a certain direction, that it is canceling out the force of my weight going down into this chair and preventing me from going downwards. This is the force that the chair is exerting on me. I am exerting a force pointing downwards on my chair, and the chair is exerting a force back upwards on me to the source of the force that I've exerted. So a more technical version and a more technical explanation of this is not every action has an equal and opposite reaction. It is when one object exerts a force on a second object, that second object exerts an equal force in the opposite direction of the first. And this explains things that kind of, if you just think of for every action there's an equal and opposite reaction, you might think of like, okay, well, let's say I'm driving in my car and I hit a bug. Like, I'm hitting the bug and the bug is like ruptured into a bunch of pieces. That's taken some force. Why didn't my car experience a force like that? Well, it did, but because your car is so much more massive, the car has exerted a force on the bug, causing the bug to explode, and the bug has exerted a force on the car, but it was so much smaller it didn't do anything to it. So it's just a very important that you realize that it's not saying that the reaction is coming from the same source as the action. It's where the two objects will kind of be, if my hand is pressing on this hand, my left one, I don't know if it's your left on the picture, is exerting a force on my palm. My palm is also exerting a force backwards on my hand. This is actually, like, as weird as it sounds, you may think like, okay, well, how does this like show up in day-to-day life? This is literally the reason you're able to walk. When you walk, and you're, after watching this and listening to this, you're probably, when you stand up to walk, you're going to be like very conscious about the motions that you're taking to walk. And it's, first of all, going to make you really appreciate like the fact that you like just learned how to do this naturally, and like it's just a thing that you like learned when you were a kid, and you've never really put into a ton of thought into your like, oh yeah, walking is this thing that I just do. But when you are walking, you are pushing your foot into the ground, usually at an angle, and that pushing is causing the ground to push back at you. You're a lot smaller than the earth though, so even though you are pushing down the earth a minuscule amount, you are being pushed by the earth, and that force is propelling you forward because your mass is so much smaller. Again, think back to Newton's second law. And so your body moves forward. And then you can place your foot, you can pivot, and you can move your other foot in front, and then you can push off with your second foot. And that second foot will cause the same action. And congratulations, you have now gone through a very, very nerdy and obscure way of explaining the fact that you are walking, literally just walking. Okay, that takes us to the end of Newton's laws. There's a couple of demonstrations, like I said, that I'm going to have posted on Google Classroom for you to do. We're kind of going to be getting to the point where, like I said, I want to be trying some new stuff, and I found a couple of online labs or demonstrations that you can do where you can kind of gather some data, you can test some calculations on some of them, and you can actually get feedback as to whether or not you're doing it correctly. So I'm going to be trying that out. You'll have to let me know how well they work for you guys and whether or not the stuff that we're doing is working. This is the conclusion of this notes, though. I hope that makes sense to everybody. In the meantime, this is Mr. Diamond signing off. I hope you have a good rest of your day, everybody.